Over the years, vehicles have become more and more complex electronically. More and more of the systems on the vehicle are controlled with electronic modules. A really big tool that we've got in vehicle design these days is CAN bus. It allows us really to distribute the processing across the vehicle and communicate between these modules in a really robust and simple way that can withstand various faults. It can withstand damage to the loom, it can withstand electrical interference, and it allows us really in a very quick way to look at what's happening across this data bus. CAN is a communication protocol that's used for electronic devices to communicate in real time. CAN stands for Controller Area Network, and these devices sit on a bus. They sit on a physical layer of wires that are laid out with a trunk and nodes. So these nodes then communicate with each other in real time via the bus itself. It's a really robust method of communication. It's really fault tolerant. It enables one wire operation if we lose connection on one of the signal wires. And crucially, it's noise resistant. That's really important to us in the automotive sector. As engineers, we have a few tools at our disposal for diagnosing faults with the CAN bus in a vehicle. Chief amongst them really is the oscilloscope. That allows us to look at the electrical signals that we're seeing on both of the CAN lines within the bus. That can tell us a lot. It can tell us a lot about what's happening on the bus. It can tell us about the nodes that are transmitting and whether they're transmitting at the right times. And it can tell us about how those messages are made up. A level above that is then a way of interpreting those signals. So we can go and you can use a CAN bus interface that we can use through a PC. And this allows us in hexadecimal to read those messages directly rather than looking at the waveforms on the oscilloscope. This too allows us to look at any faults that might be occurring. It also allows us to look at the state of the transceiver stages within each of the nodes. We add in a device onto the existing vehicle bus. We need to make sure that it's communicating in the same way that the other modules are communicating. It's transmitting at the same speed and it's transmitting the same format of messages. We also need to ensure that the IDs are not conflicting. So each of these nodes, each of the modules, has its own ID. You can't replicate IDs on a bus, and so you need to make sure that you're picking IDs for new modules that aren't already present on that bus. So the big tool for that is the CAN interface that allows us to read really what's going on in the bus. All of the electronic modules, almost without exception in a modern car, communicate using this method. So when we're looking to use CAN in our system devices, you've really got a few options of how you specify the control of those protocols. The most basic version is a low-speed CAN 2.0 protocol. That works with an 11-bit identifier, and when we're looking at between the 40 kilobit and 125 kilobit data rates, we can also look to use that single wire mode in the event of one of the failures on one of the wires. When we go to higher data rates within CAN 2.0A, we can go up to 1 megabit per second, but we do need both wires to ensure that data rate is consistent. The next option above that is CAN 2.0B. That gives us 29-bit identifiers. Because of the larger packet size then, we can be limited a bit more on data rate, but it's especially useful when we've got a complex network that perhaps has more nodes or it has more data fields that need to be transmitted. The next and most recent development with CAN has been CAN FD. FD of course stands for flexible data, and that allows us up to 8 megabits. The really clever thing with CAN FD is it is backwards compatible with the CAN 2.0 formats. The wiring in that trunk and those node drops really needs to be a twisted pair. That's a really key feature of CAN. This twisted pair allows us that resistance to noise. That physical layer also means that it's quite a simple thing to diagnose when we have faults on the wire. The termination resistors at either end, although they're giving the function of preventing reflections along the trunk, they also allow us to find any breaks in the wire. If we use something as simple as a multimeter set to a resistance mode, we can then see whether we've got continuity along the whole trunk from anywhere in that trunk, which is a really important way of not only assessing whether there's a fault with the bus, but finding where it is. We can also use an oscilloscope to look at the bus. That gives us a real window onto what's happening across the CAN high and CAN low lines. We can look at the dominant and recessive bits across the bus, and we can make sure that we haven't got any conflicts or any synchronization errors. The first step really for us to check the integrity of the bus is to disconnect one of the terminating resistors, which we've done here. We're now at the end of the bus and we're going to measure the resistance across it. The first thing and really most important is to make sure the bus is powered off. We're going to then switch our meter to resistance mode. And we know across this bus that we've got 100 ohm terminating resistor at each end. As we've disconnected one, we'd expect to see a bus resistance at the far end here of 100 ohms total resistance. And that's what we've got. So we know we've got good connection here across the bus, and we know that the far end has got its terminating resistor in place. So now we've measured the resistance across the bus. We know that we've got our termination correctly in place at either end of the bus, and we know that the nodes are connected correctly too. So what we're going to look at now on the oscilloscope is just to make sure the waveform looks healthy to us. And what I can see here is that it really does. We've got nice clear lines, we've got real good differential voltage between the bits there. What we're looking at here is the yellow line is the CAN high line, so the voltage is going high for a dominant bit. And the blue line we've got there is the CAN low line. Both of these are present, and not only are they present, they're a perfect mirror of one another. So we know our differential signal is working correctly across the bus. Let's go on to have a look at what those signals mean in the data. Now we've verified the physical layer and we've got the car powered up, we can see that we've got good communication between all of our modules on the CAN bus. So let's go ahead and just make sure we've got functional operation here. We'll check the brakes now. Pablo, can I get you just to use the brakes quickly? That's great, thanks. And we can see there that the brake signal's changing as we use it. That shows to us that the communication is not only effective, it's reliable. So now we've got all these modules communicating effectively. One of the important things to consider here is how we're multiplexing the signals together across the bus, but also how we're monitoring those for any fault parameters. We can monitor those locally at each node and make sure that all of those signals received by each node is correct and within the parameters that we set. And we can also monitor from other modules by looking at the heartbeat transmitted by each of the modules. This will tell us not only if that module has got a problem itself and is reporting that problem across the bus, but also if that bus has gone down or if that node is then missing from the bus. Without applying CAN bus to modern vehicle design, what we'd find is that the vehicle looms would be incredibly heavy and complex. We'd also lose the modularity and the ability then to add in modules easily to an existing trunk network. So hopefully that's given you an idea of how and why we use CAN bus across vehicle architecture. Thanks for watching, and don't forget to like and subscribe for more engineering insights.